Okay, so the basics of direct proportion. You need to make sure that you write some notes from this before we start doing our examples. The relationship between two quantities A and B is one of direct proportion when A increases as B increases and the graph passes through the origin. For example, distance and speed. This symbol here, although drawn by me by hand, is one that relates to direct proportion. So if I have this symbol between my variables A and B, that means that they are directly proportional to each other. This symbol is not the same as equals, so that doesn't mean that A and B are equal to each other, it just means that they are in proportion to each other. It's important to note that even though direct proportion you automatically think, okay, it has to be one variable just against another variable, so not looking at something that's to a power, it's actually not true, as long as I graph it to that power. So, for example, if I have y and I graph it on this side, and then I had x squared as that, rather than x squared being the line, well then it could be that my line, or the proportion between my y variable and my x squared, which is actually this axis, not just x, then I do get a direct proportional line. This can be written in equation form here. So I'm looking at y equals, k is my constant of proportionality, x to the power of n, where k is my constant of proportionality. So that would be the equation I'm looking at. The two variables are in direct proportion if the graph of y plotted against x to its power is a linear graph passing through 0, 0. It must be through 0, 0, which means that as x increases, y increases. Let's have a look at an example. So as I was saying, it may be that the direct proportion occurs between one quantity and another quantity raised to a positive power. Y is in proportion to x to the power of n, or as an equation, as we've said before, y equals kx to the power of n. Let's have a look at this table. If I look at this straight out, I think, I can't really see any direct relationship then. I can't go, well, 0 plus 2 doesn't give me 0, but 1 plus 2 gives me 3. But then 2 plus 2 doesn't give me 12. And if I do multiples, I'm going, well, 1 times 3 gives me 3, but 2 times 3 doesn't give me 12. So I can't really see a direct relationship there. So it could be that the relationship, or the direct proportion, isn't actually between x and y, but it could be that it's between x to a power and y. So let's have a look if it's x squared. Let's draw a new table and see what it looks like. So I've got x squared rather than x and y, which means that I had 0, 0 squared still 0, 1 squared still 1, 2 squared becomes 4, 3 squared becomes 9. And my variables for y are going to be the same. So I have 0 and 0, 1 and 3, 4 and 12, 9 and 27. If we look back to what we've said over here with our equations, we should be able to see that I'm looking for a k value, so my proportionality value. And if I actually look at x squared and y, it looks like there's a relationship there. To get from 0 to 0, I'm getting it a nice value. To get from 1 to 3, I times by 3. To get from 4 to 12, I times by 3. To get from 9 to 27, I times by 3. So if I actually wanted to work that out, that means I've got y over x squared is equal to k, which is equal to 3. So therefore, the equation here is y equals 3x squared. So I've actually got something going on with a power rather than just y equals 2x. That's okay, I can still plot it and see that there is direct proportion there, but rather than normally plotting my x against y, so on this side, if I have my x against y, and I was plotting this equation over here, then I would get a curve. Remember our parabola, right? So I don't want that, I want a straight line. So rather than x against y, I'm just going to plot y and x squared. And we've already worked out that each time I'm going up by a multiple of 3, right? So therefore, the gradient of this line is 3. If if I go over there. So like, for example, if my y value here is 27 and my x value is 9, then it is 27 divided by 9. So therefore this is going to be a gradient equal to 3, which is where my k proportionality value comes in. And therefore we can say that y is directly proportional to x squared. This means that we can find the equation that represents the relationship between two variables. Direct relationship exists if a graph of one variable against another for some power results in a straight line through the origin. A linear relationship exists if the graph is a straight line. So it just depends on what I'm plotting against what. So in this instance it's y against x squared, but I still get a straight line, therefore they are directly proportional. Okay, so let's do some more examples. In this example, I have 3 sets of tables. All of my variables are with a single power. There's no x squareds in here. Okay, so I've got P, Q, W, V, A, B. Let's have a look at this first table. Is it direct proportion? Well, first thing you should be able to see is, does it go through 0, 0, and is it going to produce a straight line? This is not an example of direct proportion because P values increase as Q values decrease, and they must increase at the same time. So before you even have to work out anything, you can just see, is it going up? Are they both going up at the same time? Does it pass through 0, 0? So for part B here, is it direct proportion? Well, again, it doesn't pass through 0, 0. It's passing through 0, 5. So I can immediately say that even though they're both increasing, it doesn't pass through 0, 0, so it's not direct proportion. So now we look at the third one. The third graph there is an example of direct proportion for 2 reasons. As A value increases, B values increase by the constant amount, and of course it is a linear relationship that passes through 0, 0. This example is, can you recognize the direct proportion from a basic graph? Even though it hasn't got any numbers or anything along my axes, I should still be able to recognize which one of these is direct proportion, because I need to make sure that it increases rather than decreases as x increases, so they both increase together. It needs to be going this direction, therefore C is automatically out. If I look at A, there's a curve in there, it's not a straight line, so therefore that one's already out. So the only one that could possibly be direct proportion here is B. Consider the situation where y is directly proportional to x squared. From that first sentence we can write y is proportional, using our proportionality symbol, to x squared. Then we read on. If the constant of proportionality is 4, so remember we use k to represent our constant of proportionality, so we can say that k is equal to 4. Write an equation to represent this variation. If we look back to what we were learning before, k is going to be my value in front of x squared. So that's just my gradient of my line. So that means that y is equal to 4x squared. And that's going to be my equation to represent the variation. Question 4. Find an equation that describes the following table. First thing I'm going to look at is make sure that they are directly proportionally. So do they increase at the same time? Yes, they do. Do they pass through 0, 0? Yes, it does. So therefore I know it's directly proportional. So I'm going to write y is directly proportional to x. Let k be the constant of proportionality. And then I can start to find the equation. So we're going back to we're going to use the formula y therefore equals k times x, because I know that they are proportional and I know that k is my constant of proportionality. Now to find k, I substitute a point in from my table. If I substitute 0, 0 in, I'll get 0 equals k times 0, which means k will equal 0, which won't give me any answers. So what I need to do is then find the next point which will allow me to solve for k. The point I'm going to use is 1, 6. That means that y is going to be 6, x is going to be 1. So I've got 6 equals k times 1. K times 1 is just k, so therefore k equals 6, which means that I can write my equation y equals 6x. And I have written an equation to represent the variation. We can then check this to make sure that it works. 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, and 6 times 4 is 24, so I know that it works for this table, so it does represent my relationship. Okay, and our last example, determine the constant of proportionality for these variables given that m is directly proportional to n. So that means that m is proportional to n, so that means I will be able to write an equation, and hence write down an equation that could be used to describe the relationship between m and n. Well, the first thing I need to do is find the constant of proportionality, and in this instance we're going to call it k, constant of proportionality. Therefore I can write an equation in terms of m, k and n. M is equal to k times n. Again, substitute a point in to find k, so I know that. I can't use 0, 0 because that won't give me a value, so we use the first point with numbers in there, which is 1, 9. So therefore I get 9 equals k times 1. So therefore k is equal to 9. And therefore my equation is m equals 9n. And I have given my equation for direct proportion between m and n. I think because of the big words in this topic, it seems more complicated than it is. It's not that difficult, it's just looking at tables of values and graphs and working out what the proportion is. So what you need to do to practice is complete the back of your booklet, 9.6 questions from Pearson 9. So it's actually in the booklet that I made and gave to you, and it's right at the end, and it's the direct proportion exercise. Can you make sure that you complete the middle band questions underneath that exercise?